Today I'm going to talk to you somewhat more about FRET, fluorescence resonance energy transfer. And today we're going to focus, in some senses, how to measure it using the donor intensity or the donor lifetime, which we had started to get to at the end of last time. And also we're going to do it not only in the donor intensity, which it decreases with energy transfer, but also the acceptor intensity, which increases with energy transfer. Also, I've given you, remember that E depends on 1 over r to the 6th, and basically that has been a complete mystery as to why it is, because it is not simply, FRET is the interaction between a donor and an acceptor, and it depends on 1 over r to the 6th, where you might expect it to depend on 1 over r or 1 over r squared if it's simply the emission of a photon being recaptured by absorption from an acceptor. But in fact, it's not the case, and we'll understand why. Okay, so again, this is hopefully all old hat to you. You have a donor, you have an acceptor. The donor emits in the green, let's say, and the acceptor emits in the red. And if they're far apart, far being much greater than r naught, they essentially don't transfer energy, and the donor just goes and fluoresces. If, however, they come significantly closer than r naught, then the acceptor ends up taking the energy from the donor fluoresces less, and the acceptor fluoresces more. And this graph showed a lot of what is going on, and the distance, as we said, the energy transfer efficiency goes as 1 over 1 plus r over r naught to the 6th. R naught is just a number and some distance that is related to the properties of the individual dyes. And if you put them close together, the donor, as we said, it shrinks, and the acceptor fluoresces a lot. And the donor lifetime also becomes very short, because the transfer of energy to the acceptor is another way for the donor to relax. What comes up here goes up here, and basically there's 2 ways for it to come down to the ground state. One is directly going down, that's fluorescence, and the other is it transfers the energy over here, and while it's doing that, it goes down. Okay? And if you have the donor acceptor far apart, the donor is essentially fluorescing just as if the acceptor practically isn't here. The donor lifetime is long, it's whatever it is. And if the acceptor, is far away, and so it's not receiving any energy, theoretically, the acceptor doesn't emit at all. In reality, in fact, it does emit some, and we'll take that into account. Okay, the way you measure it is either intensity or lifetime. That is, you measure the donor, the donor's intensity, that's I sub d, and you measure the donor's intensity in the presence of acceptor, that's I sub dA. You take the ratio of it, and you subtract it from 1, and you get, that's the energy transfer. And again, everything makes sense in terms of the units, in terms of energy transfer is the efficiency of energy transfer. So it's dimensionless. So this has units of dimensions. You can also measure it with lifetime, that is the tau of the donor or the tau of the donor in the presence of the acceptor. You take the ratio of it and you subtract it from 1. Okay? And so, for example, we're going to analyze this. Let's say we have a fluorescein molecule and we have a tetramethylrhodamine molecule. Fluorescein emits in the more or less blue-green, and tetramethylrhodamine emits in the orange and absorbs, though, in also the blue-green. So when you come and you excite the fluorescein, that's the donor, you'll get emission in this region. That's exactly where the rhodamine absorbs, although, as I said, the absorption isn't exactly the relevant term. But nevertheless, it absorbs and then will emit out in the red or orange. So what you can do is you can look in the blue-green region where the fluorescein is fluorescing. That's the donor emission. And you can look in the red where primarily the acceptor is emitting. And you can take those ratios. Okay, so this is an example of FRET. Now, has anyone done this in class where you've taken a, well, tell me, where you've had a piece of DNA which has some sort of donor and some sort of acceptor or some, have you gotten to this yet? Yes? So that's that's one person. So either he's out there by himself.
Wait, is this what we did last week?
Yes.
During lab?
Yeah.
We mixed together. I think it's just single-stranded DNA.
What's that?
We mixed together single-stranded DNA together.
Yeah. And
we mixed them, but we didn't do anything.
you mixed them, but you didn't do it. Okay. What did you mix?
Single-stranded DNA.
Single-stranded DNA.
16 base single-stranded.
One with the donor, one with the receptor.
Is that so? A single-stranded DNA that's like this, and one with the donor on it.
Yeah.
Okay. Let's say the donor is probably here. What was the donor?
It just said donor.
Just said donor. Okay. We'll put a big D here for donor. Or it's for dumb. Doesn't really know what it is. Okay. And then we had an acceptor strand also. Yeah. And so we added them in to solution, and then they'll end up binding like this. And it turns out the acceptor will also be on the end, although the opposite end. And do we know what the acceptor is? Probably not. Say 5?
I think so.
Okay.
Side 3 is the donor, side 5 is the acceptor.
Wow. That's great. Okay. So you've mixed them together, and now you're going to see them now, meaning next week, you're going to see them undergo energy transfer, because apparently, why can they undergo energy transfer? What? There's something about the dyes and something about the DNA where they'll undergo energy transfer. What are they?
The distance.
The distance. Okay, so the distance must be, the distance is what?
About 4 meters.
Okay, yeah, but so is that big or is that small or what?
Small distance?
Well, what counts is that when it's greater or larger than what?
Hopefully it's close enough that we see an overlap between the donor's emission spectra and the receptor's absorbance spectra.
Okay, yes, although that whether there's an overlap between the donor's emission spectrum and the acceptor absorption spectrum, that's going to be independent of the length of the DNA, right? So that's certainly important, but it's clearly not all that's important. What else is important? Okay, what he says or not, what somebody else explain. Why do we say that this donor and the acceptor must be closer than R naught? Yes?
Because that's when your acceptor is going to fluoresce more than your donor and you get significantly more.
That's right. 1 over 1 plus, R over R naught. Right over here. And you want to be R naught or a little bit less. So the acceptor is fluorescing a lot and your acceptor is not fluorescing a lot. Okay? And then and psi 3 and psi 5 happen to be two dyes that are quite good at transferring energy. So the R naught is 50 angstroms, maybe 55 angstroms. So if you actually are seeing energy transfer, then it says that the DNA and little linkers and so forth are less than or not. So how do we know if there's energy transfer going on?
If you see the red light coming from the receptor.
When you see the red light coming from the acceptor.
If you just see red light.
If you just see red light.
Yeah.
So you don't see any green light.
I mean, you can see green light, but
What's
the
that?
presence of red light means the transfer happened.
Okay, so this is emitting in the red and this is emitting in the green, and you're saying because you're seeing red light here, you're undergoing energy transfer. Yeah?
I guess you're going to have energy transfer if you're seeing more red light than green light.
How much more?
Depends on the distance.
Go ahead, Lynn.
You would have to get background, like the baseline for what you have with just the donor and the acceptor, and then what you have together, and compare the intensities.
In fact, that's right. In general, what you do is you need a donor-only measurement at the same concentration that you're using. You get a certain intensity there. You do just an acceptor without the donor. You get and at the same concentration, you get the acceptor fluorescence, and then you compare it to the donor-acceptor complex. And if you have energy transfer, what is going to be going on?
You're going to get closer intensity to what you get with just the acceptor.
Okay, or the donor will decrease in intensity, yes? Will decrease in intensity, and you were talking about the red a lot. What is happening? The red you're seeing is more intense or less intense?
More intense than when they're not bound.
That's right. So they come together. This is transferring some energy from over here. That causes an increase in fluorescence of this. So you get a decrease in the donor emission and an increase in the acceptor emission. Right? So, what do I have here? Here, I'm taking it as a function of wavelength. The donor emission is green. When you, in fact, bring the acceptor there, you get a decrease in the donor and you get an increase in the acceptor. Yeah? So that's what you should get. And that's just expressed this way. Or if you had a lifetime machine, which, depending on whether it works or not, you will have, you can measure the lifetimes. Tau of the donor in the presence of acceptor. How will the donor, how will that compare to tau sub d? Yeah.
Shorter lifetime?
Shorter lifetime. Is that right?
Yeah.
Yeah. In fact, the lifetime, let's say, would be 2 nanoseconds, 3 nanoseconds in the absence of the acceptor. Then in the presence of the acceptor, let's say it dropped to 1.5 nanoseconds. 1.5 divided by 3 is 1/2. 1 minus 1/2 is 1/2. So the energy transfer should be 50%, or 1/2. And in fact, at the same time, this, if these are to be consistent, this should actually drop. But this should be half of what the donor only in terms of intensity. Yeah?
Would the acceptor also have a longer lifetime than in the baseline case?
The acceptor's intensity, we'll get to the acceptor intensities. The acceptor lifetime is actually quite complicated and in general not measured. In fact, okay, so, and we'll sort of come back to that. Okay, so we have a donor quenching and the increase in sensitivity. By the way, we call the increase in emission of the acceptor the sensitized emission. That is, the acceptor is sensitized for the fact that the donor is there. So this is due to energy transfer. Okay. Oh, let's think about it, a couple of situations. Let's say you have psi3 as your donor, and you have psi5 as your acceptor. But let's say psi5 is a really lousy fluorophore. In fact, it's so bad, it doesn't even emit at all. Its quantum yield is 0. Is that common? In fact, it is common, because we said most molecules don't fluoresce at all. They still absorb, but they don't fluoresce. So let's say we'll call it psi 5 prime. So it absorbs, but it doesn't fluoresce. What's going to happen in this experiment? Is E, the energy transfer efficiency, 0, or is it not? I want you all to think about it and explain it to your partner. Go ahead. That way I can just call on anyone.
The acceptor can still take
donor times.
I mean, in that situation, you just measure, like, you know, in spectroscopy, so they have zero intensity.
You can still reach 1.
So in that situation, you can just measure that.
Zero.
You can just measure
Don't absorb at 0.
That's just all one.
like microscope. I feel like that it's just like, remember when we were in lab and it kind of said, no, you can make the, you just need a signal, you can make it any color you want. Like the microscope screens and stuff. So this could be just a thing where instead of seeing the presence of efficiency, and it wouldn't be that a matter of rearranging.
But it's the, oh yeah.
So I couldn't actually hear you guys.
You have a question or you have the answer?
Even without, I was wondering, like, you have the case where you have a donor that's not, a donor that doesn't fluoresce very much, but it can still
The fluorescence of
donate
the
the
donor
energy
just by
to
itself.
some
and then
acceptor that does
And
fluoresce.
it decreases.
You can't actually have that.
You can't.
You cannot.
Okay.
You cannot. And I'll probably explain why in a little bit. Okay, so what's the answer? So this guy is fluorescing. You bring up this guy with it, which does so-called does absorb, but it doesn't refluoresce. So is the energy transfer equal to 0? Charles?
I think the energy transfer can still be between 0 and 1. However, when the energy transfer is 1, there is no fluorescence either from the donor or the acceptor.
Okay. Why is that?
So the donor is capable of emitting fluorescence, and when it transfers all of the energy to the acceptor releases it all as heat, or through some other means. That means that when the two are far apart, we're getting a signal of fluorescence only from the donor, and then the closer it gets to the acceptor, the dimmer that fluorescence signal is until.
Okay, so what does that mean in terms of these equations? By the way, you're exactly correct. Okay? So the donor in the presence of the acceptor, it will just transfer normally. 1 minus IdA over ID. But the sensitized emission, that is the fluorescence over here, is 0. But you still get the donor quenching, anywhere from 0 to 100%. Okay? And sometimes, in fact, sometimes people do use an acceptor which absorbs but doesn't re-emit the light. Okay. So now we're going to measure the energy transfer, not by the donor quenching, but by the increase in the acceptor fluorescence. And the question is, what is the formula in that case? And it's a fairly complicated formula, though you'll see that it does actually make sense. Let's forget about the quantum yields of the acceptor and the quantum yields of the donors. Let's just forget about it. Let's say it's 1. What does this say? This is I, the intensity of the acceptor, in the presence of the donor, divided by the intensity of the donor in the presence of acceptor, plus, again, the intensity of the acceptor in the donor. So, again, let's look at this, and first, does it have the right limits? You know, does it go to 0 when you expect it to go to 0? Does it go to 1 when you expect it to go to 1 and maybe be at half when you expect it to be at half? Again, let's not worry about the quantum yields. So, okay, why don't you go figure this out, whether this is reasonable. When is E equals 0? When is E equal to 1? And what does this mean? This divided by this whole thing. Go ahead. Go work it out.
The acceptor A sub D. Does that necessarily mean that A?
But by the way, I give you these PowerPoint slides. They're on the web, just in case you don't want to write.
Otherwise, as you take the 0,
Well, you asked whether if you wanted up to 0.
And then you would
well, actually, with non-negative stuff, that's necessarily true. Like the energy could be lost.
Yeah, it's like from it's like from
I think
both the infinity term numerators in the respective numerator and denominator.
What is I? Right. That didn't change.
Well, what all of them represent as constants, like i.e. the intensity of
So if that's the case, what limit would you take?
overcharge of A.
Do you know?
If you take D sub A.
No, we're thinking.
Okay.
What are they?
Imagine the donor is fluorescing and the donor is fluorescing, and you know they're well separated from each other. So you have no direct acceptor fluorescence. So if they're far away, you're going to get just the donor fluorescent, zero acceptor. So that's I sub D sub A. And I sub A sub D is, in that case, 0. Right? Now if you bring them closer together, what's gonna happen? Okay, it'll go up. Right. That. So this is now no longer 0, some finite number. But okay, but you saying, but the donor still has some fluorescence. How much is it? Okay, so How'd we do? That good, huh? Come on. So let's imagine you have a donor and an acceptor die. You come in and you excite the donor, and it has some intensity, and the acceptor is there, and it doesn't have any intensity. It doesn't absorb at that frequency, right? So in that case, you have what? IA sub D, that is the intensity of the acceptor in the presence of the donor, will be what? 0. So the energy transfer is 0. Okay? Now they're close together. Let's say the energy transfer is 50%, or 0.5. 0.5, what is going to happen? What's going to be the intensity of the donor and the intensity of the acceptor? What is it? It'll be the same intensity. Okay, so what? The intensity of the acceptor is now equal to what? The intensity of the donor. So what E is, let's say initially it was, let's say 100 units, and it goes down to 50 units. So this is 50 units. The donor decreases, and it's 50 units. And this is 50 units. So 50 divided by 100 is 0.5. Good. That is making a lot of sense. Okay? And so if you put them together, they're even closer. What happens then? The intensity of the donor in the presence of the acceptor is what? Going down. Let's say if it was 90%. What will the intensity of the donor look like? It's transferring 90% of its energy. What? How much? Initially it's at 100 units, and then when it's transferring 90% of the energy, how much is it fluorescing? 10. Okay? It's gone down to 10. And what about the acceptor? The acceptor has taken up that energy. So how many units of fluorescence is in acceptor going to have? 90. Exactly. So the energy transfer is then what? The energy transfer is the acceptor, we said, was 90 divided by the intensity of the acceptor, of the donor, is what? Well, the donor in the presence of acceptor is 10 plus 90. So that's 0.9, well, not 0.9%, 0.9. Looks good again. So this is, we're looking at the sensitized emission, the relative heights of this compared to the relative heights of the donor. and the presence of the acceptor. Now, wait a second. Yeah?
So what about the non-radiative pass of the acceptor? What about the energy wasting in that part?
Okay. We're assuming, in this case, the donor, was transferring energy with, let's say, 90% efficiency. So 90% of that increase, it decreased here, immediately went into all of it went into fluorescence of the acceptor, right? What if the acceptor, it takes the energy, but doesn't fluoresce? Then we have a problem with this, don't we? Let's say the acceptor's quantum yield, that is the probability that it will emit given that it was given some energy, seems like it has to come in here in some fashion. Let's say its quantum yield was 0, right? In which case, what we said is the donor still feels energy transfer. It decreases in fluorescence, but the acceptor, we're saying the acceptor emission is now 0. So in this case, if we forget about the quantum yields, say the quantum yield of the donor is, let's say, unchanged, but what happens? The quantum yield of the acceptor now is 0, right? So what is this number? What is this number? 0? Well, actually, it's infinite, right? Something over 0 is infinite. This number is still finite, and so you get something like 0 over 0, and I don't know what that is. That is, if the acceptor doesn't fluoresce, in fact, at all, you don't get any sensitized emission. And so, in that case, this formula doesn't really work. But in fact, we can correct for the formula where we can take into account the fact that the acceptor is not a perfect emitter. So it takes like that 90% of the 90% energy transfer and emits not 0, but emits something. And if the efficiency is like 1/2, then in fact you divide it by 1/2. Or if the efficiency is truly 1, you have just 1 here, and then 90% energy transfer, 90% drop in the donor, and everything appears in the acceptor. So that's why you actually need these quantum yields in there.
So by dividing the quantum yield, you actually fulfill the requirement of energy conservation in that equation, right?
That is correct. That is correct. These are, in fact, the number of excitations total. This is the number of excitations of the acceptor in the presence of donor. This is the number of acceptors in the donor in the presence of acceptor. And this is the number of excitations in the acceptor. Actually, it's interesting. So there's actually a physical point there where the energy transfer is equal to the number of excitations of the donor divided by the total number of excitations. It's actually measured in terms of excitations, not in terms of emissions. That's actually frequently a point that is not appreciated by people. But so it is important to not only measure the intensities, but actually to measure the quantum yields. Okay, so there's a clever way of measuring the energy transfer by the sensitized emission. And I was going to go through that, but for now, I think I won't. I think I'm going to go through why the energy transfer goes like 1 over r to the 6th. Okay. So energy transfer goes like 1 over 1 plus r over r naught to the 6th. Why is it that? And for those everybody should have the ability to understand this. It helps that you have, let's say, intermediate E and M. But if you haven't had that, then you can just take it at face value. Okay. Remember, traveling photons goes as 1 over r squared, right? So if you have a photon, let's say a light bulb, and you put a circle around it, then you get out a certain number of photons, that are going through your surface, right? Now you decide, in fact, to put a big circle around it. You still get the same number of photons in the small circle and the big circle, right? Therefore, the photons must go like 1 over r squared, right? Because that surface area is going like what? What is the surface area? 4 pi r squared. So we've increased r squared so that the photon density has decreased by r squared. So, okay, that's right. So if the photon density goes like 1 over r squared, and if you remember from your basic E and M Maxwell's equations, what does the electric field go like? The electric field, how is that related to the energy density? It's like cruel, huh? Good. The energy density goes like the energy squared. If that goes like the E here is the electric field, not the energy transfer. So E goes like 1 over r, and so the energy density is going like 1 over r squared. Okay? Okay. It turns out that this is only approximately true. That is, we put a bag around it, and then we put another bag, and we saw that the energy per area is going as 1 over r squared. It turns out that if we used a really tiny bag, the electric field wouldn't go as 1 over r. If you remember from your days in E&M, that is, in the far field, it goes as 1 over r. In the near field, does anybody remember what the near field electric field looks like?
I'm guessing 1 over r squared, r to the 6th.
Close, but actually not quite.
Minus r to the 12.
Oh,
There was something like that.
yeah, that's right. How many of you were physics majors as an undergrad? And it's, ooh, shame. Okay. In the near field, it turns out there's electric field that goes as 1 over r cubed. It still goes, it has basically the 1 over r cubed plus the 1 over r component. See, this shows you that, well, most of the things that they've taught you as an undergraduate in physics is like whatever. There are a few things that actually matter. I don't know if it matters, but 1 over r plus some number and this. So this is what the electric field looks like. And it has to have, what do we mean by close or far, the size of this bag? Well, somehow it must relate to the wavelength. And so, in fact, you have this, and, well, probably you have this, again, for units. So what happens when r is much less than lambda? When this number is really small, how does this compared to this? Okay, let's do it another way. When this number, lambda over r, is much greater than 1, this number versus this number, which term is going to dominate? Yeah. What's that? The second. Okay. For lambda over r much greater than 1. That is, the distance is much greater than lambda. You're putting your bag around here at some real macroscopic distance. And this is what you feel or see as photons. Now, let's say you put your bag really close by. That is, if lambda over r is much less than 1, then what are the relative sizes of these? They both exist, but in terms of the size, which is going to dominate? What? The first one. And this is r much less than lambda. Okay, what is lambda? Lambda is the wavelength of oscillations, the electric field. Lambda, we said, is like 500-600 nanometers. So which is the relevant term in terms of the interaction between an acceptor, which is producing this electric field, which right nearby is 1 over r cubed, and far away is 1 over r. So is you have the donor and the acceptor. For energy transfer, what are we talking about? What are the distances involved? What are the distances? Huh? Okay. Yeah. We're talking about the donor and the acceptor being like 50 angstroms or 20 to 80 angstroms kind of thing. So that's much less than r, is much less than lambda. So this is what actually counts. The electric field induced by the acceptor in the near field looks like, whoa. R much less than lambda. No. You guys, you let me pull a fast one on you and on me. If lambda over r is much, what? There's something funny going on here. Yes.
Write it there, please.
Oh.
There's too much reflection. I think it's
Oh, sure. Oh, you can turn on the lights.
Oh, yeah. No, I can see that.
And if lambda is much greater than r, which dominates, and if lambda is much greater than r, which term dominates. So lambda over r is much greater than 1, and here lambda over r is much less than 1, right? So in which case, if you have a number x versus x cubed, and x is much greater than 1, which is dominating? X cubed. So in this case, E is going like lambda over r cubed. Yeah? And here, the E is going like lambda over r. They're both present, but we're just talking about which term is the dominating term. Okay. So lambda over r.
You see the other one?
Well, let's see.
Do you have to flip the two terms for lambda and r?
Because if lambda over r is much smaller than 1, that means r is... Oh, no. That's good.
That's good. This is exactly what I I messed up over there. So is this good? Okay. So in this case, lambda is, let's say, 5. So this is like lambda is much greater than r. That's the same thing. So this is like 500 nanometers. So in this case, r, you must be greater. R is less than 500 nanometers. Wait. Jesus. And this is lambda is greater than r. Yes? And so, okay, and here then lambda is much less than r. Okay, so now we say (500 nanometers) is much less than r. So we're talking about 500 nanometers, big distance. So this case is photons. It's emitting photons. With this case, where you're really tiny, this is no photons emitted, but you have lambda is much greater than r. You have 500 nanometers is much greater than, 20 angstroms or 80 angstroms, and that is 2 or 8 nanometers. So this is the term that dominates. So the electric field looks like 1 over r cubed. Right? Okay. So these molecules are like little dipoles, where the energy goes like the dipole moment times E. Therefore, the dipole emitting energy looks like P over r cubed. The absorption looks like P times E. I'm afraid I'm going fairly fast. So the light emission looks like P times E times the emitting P times E, which is P sub absorbance, P sub emission times energy squared. But the energy, we said, goes like 1 over r cubed. The energy transfer goes like 1 over r to the 6th. So this is why you always have that. The way you can test this is you have an acceptor, you have a donor, and you have an acceptor. See how much energy is happening here, and then double the distance. And the amount of the energy transfer should go like 1 over r to the 6th. And that's exactly what you actually find with energy transfer. And it turns out, so it goes like r to the 6th. It also goes with something that depends on the dipole strength of the emitter times the dipole strength of the absorber. This unit must combine to have an r to the 6th units. So this is equal to r naught. Is equal to r naught to the 6th over r to the 6th. And so r naught gets larger if the donor, that is the absorber, has a big dipole moment, and gets smaller if it doesn't have. And similarly, in terms of the emission. Okay.